This is the last video for reviewing common themes and free response questions for AP Calculus. We're going to look at an area volume problem. The area volume problem has shown up 10 times in the last 10 years. So you can pretty much count on having to do an area, calculate an area or a volume, either of revolution or known cross-section. It's pretty split 50-50 for no calculator, 6 calculator. As part of this problem, you'll be expected to calculate intersections of functions. So setting the two functions equal to each other and solving for the x values where they intersect. Set up or calculate the area of an enclosed region. So from between those two endpoints, set up and calculate a volume. Having a known cross-section like a right isosceles triangle or a semicircle or square, rectangle, something like that. Set up and calculate a volume of revolution. So, revolving around an axis or a line parallel to one of the axes. And then writing an integral expression to find maybe a vertical line that splits the region into two, or a horizontal line that splits the region into two. Just kind of looking at this big picture, we know that when we do calculate an area, we know that we're taking the top curve minus the bottom curve. Sometimes we have to split it into two expressions if one of those changes, or if they cross and switch assignments. For volume, in either instance, remember volume is found by integrating an area function. So if we're revolving, that means the expression is going to be a pi r squared, where r is going to be the function. If we have a known cross-section, then we have to develop an area function using a geometry formula for that specific shape. So let's take a look at this question. It's a question 2, which means it's a calculator question. And we have this region, and it's enclosed by y equals 4 and f of x equals x to the 4th minus 2.3x cubed plus 4. And we've got two volume questions and finding that vertical line that divides it into two. So we take a look at that first question. And, whoops, I have a mistake here that you're not supposed to see till the end, but the first question is finding the volume that's generated when it's rotated. So if we're rotating here, we have to think we're making a circle about the line -2, which is down here. And so if we're making a circle, then it's a pi r squared. So if we look at the animation up here, here's that region, and now I'm going to spin that region around this line here, which is y equals -2, and we're going to end up with this washer that's got a curved inside and a flat outside. So this purple inside is curved, that has this contour, and the orange exterior is flat. So first thing you want to do, since it is a washer, is you want to identify the outer radius and the inner radius. So I've tried to color code this here. And so the outer radius is, we're measuring from -2 to the outer portion of the shape, which is that horizontal line. And then the inner radius, we're going from that purple curve back to the axis of rotation, which is that y equals -2. So I'm going to first do a calc intersect to find these 2 points of intersection. And so I've put y1 and y2. I've put the functions into both y1 and y2, and then I can go ahead and do a calc intersect to find that these 2 points are 0, 4 and 2.3, 4. And then I go ahead and identify the outer radius. So we're going to spin this around And so that outer radius has, we can always take the top function minus the axis. So 4 minus a negative 2. So that's a distance of 6. So think of this as the center of the circle. That's this black line here. It's the center of the shape. And then coming out here is the outside flat surface of that shape. And then the inner radius comes from the axis of rotation to the purple shape. And so that's going to be the function, again, minus a negative 2, the function minus the radius. And so we have the function here. Minus the radius is just going to be a plus 2. And so simplifying it, we get that distance for the inner radius. And then we can go ahead and put it into our volume expression. So if you can see, we have a pi r squared for the outside and a pi r squared for the inside. And we're going from 0 to 2.3. So those are x lower and x upper bounds. So here's your correct setup. And so if this were a write but do not evaluate question, this is the setup that they would grade, and they would make the points would be assigned to you based on whether or not you had a pi, and whether or not your bounds were correct, and then whether or not these functions are correct and squared, and then whether or not you have your dx. To talk about now the actual problem of finding the value of that volume using our calculator, since it is a calculator question. What we're going to do is we're going to go ahead and put the two functions, y equals 4 and f of x equals that polynomial, into y1 and y2. And this will allow us to do the f int a little quicker. So, and you should already have these in anyway because you had to find these points of intersection. So I go ahead then, and from the previous page, go ahead and put in the pi times, don't forget the pi, it's really important, an f int here, and then I could have put y1 here, but it was just as easy to type 4. So 4 minus negative 2, there's the axis, right? We're always subtracting that axis. And that's the outer radius, and then the inner radius here, so we're subtracting y2 minus a negative 2. So here's my y2, let's maybe get that by using the bars key, and then subtracting the axis here, and then squaring both, putting a dx there, and so I get that value for the volume. So I always want to convey what I'm thinking on the AP tests, so I should be writing volume equals, v equals, and then this expression for the setup. In this case, you don't really need to write it, but you probably already have it written down anyway, just by figuring out the problem. And then the answer, 98.868, those 3 decimal places correctly rounded. For part B, it's asking you to take this region here. It's a base of a solid. So here's the region here. And we're going to put a cross section that's an isosceles right triangle. So we're going to start building isosceles right triangles here across that flat region. And so you can kind of see what that ends up being. We end up having a shape that's that's sloped on one side because of the hypotenuse, and it's vertical on the other 2 sides because of the legs. And so there's your isosceles right triangle. You got a vertical edge going along the curve, and our hypotenuse going along the line y equals 4. And we could actually reverse that if we wanted to. We get the same volume. It would just be a different shape. So again, I'm going to take you through a write but do not evaluate, just to set up the question as if this were no calculator. So first we want to find an area function. So we know the area of the triangle is 1/2 base times height. So the base of the triangle is going from the horizontal line down to the curve. So that base then is 4 minus the function, right? This is 4. This is the function here. The function is always measured from the x-axis. So this distance here is 4 minus the function. So then your area then is half base times height, and since it's isosceles, base and height are the same, so it's half base squared. So, so that's your area function. You can just throw that right into your integration. So your volume then is 0 to 2.3 half base times base, 4 minus f of x quantity squared. And the nice thing is, as long as College Board has said, has decided to call this f of x, you can use f of x in any expression. So you don't have to put the polynomial here if you don't want to. You can just leave it f of x because they have defined that in the problem for you. So this would be the correct setup with upper and lower limits, correct area function, and a dx. And then now what we really need to do, we can simplify this if we want to. So I did throw the polynomial in here and simplify it. And I did the same here. And then we could, have this as a setup as well, which would be correct. So I'm going to go ahead then, and since this is a calculator question, just do an f int. So you notice I have 0.5, and if you remember, y2 was 4, y1 was the polynomial. So I just use my bars key, makes it look a lot cleaner. Square it, put in my dx, and there's the volume of that shape. So when we round that correctly to 3 decimal places, it's 3.574 for the volume. For part C, we're trying to find a vertical line. They even tell you it's vertical. That's kind of nice. Takes the guesswork out of it. At location K, somewhere between 0 and 2.3, dividing this into 2 equal regions. So here's my vertical line. Its question is where does it need to go? Okay, so it's going to keep sweeping across here to make the left area and the right, or the left region and the right region equal. So we know area between two curves is just subtracting the top minus the bottom in an integral. So there's my top, again, there's my bottom. I'm just calling it f of x. I can do that since it's been defined as f of x in the problem. I don't have to put the polynomial there. So there's the entire region because I'm going from 0 to 2.3. So if I want an expression to divide this into 2 equal regions, then I need to locate this location K somewhere in here. So here's the left region from 0 to K, and that should be equal to the right region from K to 2.3. So there is, notice it says right, but do not solve. There is the correct expression. We have an equation involving integral expressions, and if we would solve this, we would get K. Occasionally, they do have you solve it. So I'm going to go through what has to be done to solve it. The first thing you want to do is, take one of the regions. I'm going to take the left region from 0 to K. And, okay, I said equal the right reason. I just kind of restated this. Notice I put the functions in. 4 minus this is just x to the 4th minus 2x cubed. So we're kind of going after that. What would be nice to know, though, if we want to find K, is find the area for the entire region first. So actually throw this into your graphing calculator. So that's what I've done here. So the entire region is 3.218 square units. And we know that if we divide each side into equal parts, then each side has to have half that. So each side has to have 1.609 square units. So the idea then is one side of the region could either be the left side or the right side. So all we're going to do is trial and error with a value here for K to get the answer on our calculator to match this. So so here's just basically what we've discussed on the previous page. And let's do some trial and error here. So I tried 1.75 and I got 2.110. That's too big. I tried 1.5, I got 1.392. That's too small. And then I tried a bunch of other ones after that, and I finally figured out that 1.5783 got me pretty darn close. At least the 3 decimal places matched. You can get the first 3 decimal places to match. then we're close enough to get this correct from a rounding standpoint. So the answer then is, I have a k value of 1.5783, which is about right where this line lands, about right here. The last question type that you probably will run into is something we call an accumulation and drain question. It's shown up 8 times in the last 10 years. Typically it's on a calculator question, sometimes on no calculator. So it's typically a calculator portion. Basically, they want you to do an FN int to accumulate something. So we typically might have a rate function, and then we have to integrate that to accumulate something. For instance, like sometimes we have a rate of snowfall, and so we integrate that to figure out how much snow has fallen in a certain time interval. Sometimes they have you do an n-deriv to find of a function, if they give you a function, to find the rate. So for instance, like maybe we have a function for the snow depth, and we want to know how fast the snow is falling at a particular point in time. Sometimes we want to know the rate of a rate. So for instance, maybe we have the rate of how much snow is falling, and we want to know where that rate is the heaviest, where it's coming, when it's coming down the fastest. So we would do a derivative and then look for a max. Sometimes if they have you do an FN int, they'll definitely have you do an average value. Since you've already done the FN int, you can then just divide it by the interval width to get the average, like for instance, the average snow depth or the average rate of snowfall over a certain time period. I kind of alluded to it with the n-deriv, finding a maximum or a minimum rate. You know, when is the snow falling the heaviest? And then sometimes they'll have you optimize an expression. So they'll have a condition where they have, you know, for instance, like snow falling and it's melting. Or I think we had an example in the review where we had people entering the store and people leaving the store. And so when did we have the most people in the store? So this one would be like, we have snow falling, we have snow melting. When is there the most snow on the ground, or something like that? So an optimization question. So we'll look at this next question and try to hit most of those typical things to ask. So this is a question number 1. It's a calculator. We've got we're working here at a gravel processing plant. We got gravel coming in. It's unprocessed, so it's like big chunks of concrete. And we send it through a processor that breaks it down at this rate. You notice it says the rate in tons per hour, which this machine can process gravel. And this machine runs all day. At the beginning of the day, the plant has 500 tons of stuff already there, ready and waiting to be processed. And we know that during the day here, the plant processes gravel at a constant rate of 100 tons per hour. So so we have gravel arriving, and then here we have some information that tells us how quickly we're getting rid of that unprocessed gravel. So we have a accumulation and a drain, so to speak. So for part A, it says find the rate that to find the derivative of this function. So so we want to basically figure out the rate of this at hour 5, so just after lunch, so to speak, using correct units to interpret your answer. So there's a lot of interpretation that goes along with these types of problems. So being a calculator problem, we want to find the derivative of g of t, so we're going to use our n-deriv. So again, I'm going to put the function into y1. This happens to be a trig function, so make sure you're in radians mode. And then that makes my n-deriv look a little cleaner. So I'm going to go ahead to do my math n-deriv. And I'm going to use my vars key to put y1 in there. I'm going to evaluate it at 5. And I get an answer of negative 24.5875. And so correctly rounded, then that's minus 24.588 tons per hour squared. So if we think about that, differentiating introduces another rate of time. G of t was already a rate in tons per hour. So this is tons per hour when we take its derivative. So notice that since, it's important when you're being asked to interpret your answer that you use the notation that the problem stated. So here's G prime of 5, just like the problem stated. Here's my answer with units, rounded to 3 decimal places. And now for the interpretation, we have to kind of pick through this and give each of this a kind of a verbal explanation. Units here are nice, but not totally necessary. So the explanation here is 5 hours into the workday. We have gravel arriving is decreasing at 24.588 tons per hour, or per hour squared. For part B, it says find the total amount of unprocessed gravel that arrives at the plant during the workday. So let's just pretend that maybe this machine broke down, but we still have gravel coming in. So arrival means we just need to accumulate this function. So here's our accumulation portion of the question. So we know it's a rate, so we need the integral of that, and we already have the function in y1. So we're just going to do an f int from 0 to 8, 8-hour workday of y1, and we get 825.551. So again, I'm kind of conveying what I know here. Accumulating G of t, we have 825.551 tons, because this is tons per hour times hours is going to give you tons. And it just says find the total amount. So we found it. That's all we really have to do to answer this question. So just to kind of add a little extra here, this is the amount that arrives in 8 hours, but we already have 500 tons there. So they could ask you how much is in the plant, which means we'd have to add the 500 to that. So again, here's where we have a reference. We got the answer. Units are always nice, but they don't ask you to put the units on, but it's always nice to do that, and we've got that correctly rounded. For part C, C says, is the amount of unprocessed gravel at the plant increasing or decreasing after 5 hours? So now we have to consider the fact that we're asking for the amount of unprocessed gravel at the plant, which means we've got gravel coming in, unprocessed gravel coming in, and we have processed gravel going out. So this is our, what I call accumulation drain sort of scenario. So we have to take that accumulation and subtract off this, this drain. So it's an amount, which means the amount of unprocessed, we have the rate of unprocessed gravel minus the rate of gravel out, or processed gravel, so to speak. So the rate of unprocessed gravel in, we did that in part B. I'm going to show this graphically. So notice my window here. I went from 0 to 8. That domain coincides with this. I have a y min of 0 and a y max of 150. And so here, excuse me, here is my rate of unprocessed gravel in. So at 5 hours, there's how much unprocessed gravel that has come into the plant in the first 5 hours. So, excuse me, I said that wrong. This is a rate. So this is the rate of gravel coming in at 5 hours into the workday. So the rate of unprocessed gravel, that means 5 hours into the workday, I've got 98.141 tons per hour coming in. And then we know the rate going out is constant at 100. So that's the rate that we're removing gravel. So as you can see, we're removing it faster than it's coming in, okay, so at that point in time. So in fact, we're losing 1.859 tons per hour at that time. So the rate is decreasing. And we've shown the work, if you've shown that G of 5 is this much, you don't have to necessarily show the sketches, but it doesn't hurt. And you identified that the gravel out is that much, and you've shown the subtraction. then you've shown the work that leads to your answer. So all you have to state then at the end is that it's decreasing. Part D, it says what's the maximum amount of unprocessed gravel at the plant during the hours of operation? Justify your answer. So we want to know when our biggest pile of unprocessed gravel is sitting in the plant. And so this is our optimization problem. We want to maximize that, that accumulation drain scenario. So we need the integral then, because we're talking about the amount of unprocessed gravel, and G of T is a rate. So we have to integrate this, and the 100 tons per hour is also a rate, so we have to integrate both of those. And then when we do that, we can look for the maximum, the peak, so to speak, of that, of subtracting those two functions. So, and then that would be rate in minus rate out. That would be accumulation drain. We have to remember that originally we have 500 tons sitting there in the first place, since we want the amount of gravel, not just the what's going in and what's going in and what's coming out. So we're trying to maximize this function. We start with 500. We bring in gravel at a rate, and we remove processed gravel at a rate. So when we integrate those two rates, this is the amount we start with, this is the amount that it changes by, and we want to maximize that function. So if we want to maximize that, that means we're looking for a hill in that function. So we can do this on our calculator, which is really nice. So let's take a look at this. I am putting in, I've got Y1, I've got our rate that the unprocessed gravel is arriving here. And notice my Y2, I've put this entire maximizing function in there, 500 plus the integral. And I can put an integral right into Y2 if I just leave the variable, top variable X. And the bottom variable is my start point, which is 0. And then I've got just Y1 minus 100, which is G of T minus 100. And then notice I turned off this one because I don't need it. I just need to maximize this. We're optimizing this relationship. So we're looking for that hill there. So I turn off Y1. I leave this undefined so it graphs it as a function. I'm going to put that in my graphing window as a minimum. I start at 500 and then I accumulate this. So when I graph that, I'm going to set my window from 0 to 8. I'm going to start my Y min at 500, and I just arbitrarily decide to go up to 1,000. Hopefully that will be enough, and I won't have to adjust that. So when I do that, I get this. And so here's my peak. Here's my maximum, excuse me, my maximum amount of unprocessed gravel in the plant. And so that occurs then right here. If I do a second calc max, I can see that it occurs 4.923 hours into the workday. And the maximum amount of unprocessed gravel in the plant is 635.376 tons. And as far as justifying the answer, if this is set up where you have this optimization or this maximum function here, then that is your justification. You can just say that the derivative of that function must equal 0, and this is the condition that satisfies that